we learned the simplex method. Is that right? So we took the starting point, that is, if you manage to write your LP problem in canonical form, where the constraints are in canonical form with a feasible basic solution, and the objective function written in terms of the non-basic variables, right? And then we could put it into the Tableau or into LP Assistant, and we can carry out this procedure to find solutions, provided nothing goes wrong. But things can go wrong. We'll deal with that later in the optimistic case. Okay. But then there is one thing, actually, one quite big thing we have not really talked about. That is, if you are given a problem only in standard form, not in canonical form, how do you put it in canonical form so you can start the simplex algorithm, right? That's a kind of a big step. It's not obvious that you can just do it. Okay, so today we'll be learning one technique, and later on this will be built in together with the rest as one way of rewriting your problem from a standard form to a canonical form. Okay, let's see. So this will be the 3.6 in the book, and the technique is to add bunch of many, as many as needed, so-called artificial variables. Okay, and then we'll see. So this, I say, in the end, it's some kind of a trick, or you want to say technique, okay, to put LP into canonical form from, so we need to say, from where do we do that? From a standard form. Okay. So you have a problem in standard form, meaning the constraints are written in equal sign, not in inequality. If it's inequality, you introduce slack variables and make it into equal sign. So it's a standard form we start with, okay? Right. Okay, so let's say with this technique. So let's say I have a standard form problem. Standard form, and let me concentrate only on the constraints first, okay? And then later on, that's the first stage. We want to put the constraints in a canonical form from a standard form. So let's say I have the standard form problem. Let's say it's written like this: A11 x1 plus. So I have n variables, right? And I can write down, let's say I have m constraints, so I can go all the way to the m. Okay, so these are my constraints. So of course, all the variables have to be non-negative. Understood. We don't put that up. Okay. So, I would make a further kind of assumption. I would assume that the right-hand side is non-negative. I can always do that. If one of the BIs shall be negative, I can multiply the equation by a negative sign and make that positive. Is that clear? So I will now assume that, okay, let me put it here. So I will now assume all the BIs are bigger than or equal to 0. I can do that. That's not a big deal. That's a simple manipulation, right? So let's say all the right-hand side are bigger than 0. Okay. Now I want to introduce my artificial variables. So introduce artificial variables. Is that okay? AV, artificial variables. I'll call this AV. I have to write lots and lots of artificial variables today. So let's say that's an bunch of artificial variables. I will introduce one for every equation, okay? So which means I need to put m of them. So I will call them I would just make the index bigger, so n plus 1, n plus 2, to n plus m. These are variables. For my problem, then of course they cannot be negative. Is that right? That's always understood. Okay. And then I add 1 on each equation. Is it okay? So let's call this constraint set 1, and I have a second set of constraint, which is A11. So the first n terms are the same, and I just add 1 more, n plus 1, that equals to B1, and then the last one, M1, X1 is not changed. Okay, and then this will be kind of a going down, diagonally down by the way we write it, n plus m equals to b m. Okay, so let's call this set constraints equations system number 2. Okay, what is special about this number 2? Anyone wants to comment? What is so special about it? We're not building connections yet. We just observe this system 2. Is it in canonical form? Is that what we want to do? Do you think the 2 is in canonical form? If yes, what are the basic variables? So how do you check if one variable is a basic variable? You look at the column. That variable should have coefficient 1, while all the others are 0. Is that right? So I see that all the new artificial variables I just added in can be used as basic variables for system 2, and the system 2 is in canonical form. Is that right? And also the right-hand side is all bigger than or equal to 0, which means the basic solution will be feasible. Is that right? I'm not speaking French, right? We know what these means, right? Okay, let's make that observation. So that's important. So observation 2 is in canonical form. We agree with the basic variables. Those are exactly the one that I add in my artificial ones. They are all basic now. Okay? And what about the basic solution? So this is observation 1, and then the second dot. And then we see that the associated basic solution, what is the basic solution with this? Well, the basic variables will take the value on the right-hand side. All the non-basic ones will be 0. Is that right? So the basic solution will be 0, 0 for the first n of them. So there will be n of them. The number is n from x1 to xn. And then the rest will be taking the right-hand side. Is that right? And this is all bigger than or equal to 0. So it's feasible. Is it correct? So this is a feasible one. Okay, so we found we wrote it into a form that is canonical with feasible basic solution. That sounds like a good starting point for some linear programming problem, right? So we need to understand, okay, what linear programming problem can I associate with this as my constraint that will help me reach what I want to achieve? Okay, so keep your mind clear. What we're trying to do, I want to put 1 into canonical form. That's the final goal. And all this is trying to get into that. Okay. Okay, so this looks like a good starting point for some linear programming problems. So let's see. Now, I would associate system 2 with a linear programming problem. So all I need to do is put up a objective function. Is that right? I need to find something to minimize. Let's see. I introduce this term. minimize something I call it W. W is simply adding up all the artificial variables that I just introduced. Is that okay? I try to minimize that, okay? And subject to the constraints in 2 that I have there, okay? And of course, all the x's are bigger than 0. So, and let's write it. x1 all the way to xn, all the way to xn plus m are bigger than equal to 0. Okay. How about I find this problem? I want to minimize that. Okay, let's see, I want to solve this minimization problem. Then we'll come back to the meaning of it in a short bit. Okay, so now I have an objective function with the constraint, which is already in canonical form. If I want to solve this with simplex method, I just need to make sure that my objective function is written in terms of the non-basic variables. Is that right? Right now, the objective function is the sum of all the basic variables, which I don't want because I cannot use it. I need to manipulate that. Okay, so I need to put this, to put the LP, this problem here, in canonical form. So we need to do this step. Rewrite W in terms of all the non-basic variables, which means from x1 to xn, all those that's not there. Is that right? So x1, xn. Okay, so, but that's just a manipulation, isn't it? It's basically just a pivoting process to remove that, or you can observe directly from 2. I can do this simple manipulation. What I do is I add up all equations. Okay, add up all the left-hand side and all the right-hand side, and I get a new equation. Can I do that? So let's see what we have. Add up all equations. Okay, in the system number 2. So the system is written in an organized way. So you see each column has the same variable, and in the end, you would just have to add up all the coefficients in front of that, right? Say, in front of x1, you have to add up all these a's, right? And then xn, you have to add up all these a's. And then for the last m terms, each column will contain only one x. Is that right? And the right-hand side, you have to add up all the b's. Okay. So allow me now to write it in this particular way. Let's say I add up the first column and I get some number in front of x1. And may I call that number negative d1, x1. There's a reason why I put a negative sign, because later on it will appear to be a positive sign. Okay? So let's say this is what's in front of x1 after I add it all up. And then I will have something in front of x2, which I call it negative d2, all the way to the last one will be dn, xn. Okay? That will be the first n term. And then the next n terms will be simply summing up xn plus 1 all the way to xn plus m. Is that right? That will be this part after. These are all the artificial part. Okay? And then I add up the right-hand side, all the b's, and I call this number, it's some number, the negative w0. Okay, it's just a number, I call it. With a concrete example, you see more clearly what they are. Okay, so let's specify what is d1? Well, d1 is just adding up all the coefficients, but take the opposite sign. So it's the negative of a11 plus a11 2, 1 plus all the way to a m 1. Is that right? You can generalize to find out the general term. Let's say the I, what would it be? Well, we just add up the coefficient of the ith column. So I will have a1i, a2i, all the way to a m I. Is that right? I from 1 to you just add up all those n columns, and you get those numbers, and you make them negative to put it there, right? And also the W, 0, is now just the sum of the right-hand side, but taking negative values. So negative of B1 add up all the way to Bn. Is that okay? All right. So I see now, okay, all these are there, and then I see that these final sum from xm plus 1 to xm plus m, and that is exactly my W. Is that right? That's the one I'm trying to minimize in this problem. Okay. So I could maybe arrange terms, move the W0 to join the W, and put this on the other side of the equation. Then I get all plus signs. Is that okay? So rewriting everything, I'll have the following. I'll have d1 x1 plus d2 x2 plus all the way to dn xn, and this will all be 0, and I will have w0 plus w. Okay? Now you see w is expressed in terms of all the non-basic variables here. Is that clear? That's one step towards it. Okay? So let's call this star. Okay, so we can conclude now. Now the linear programming problem of minimizing W with the star here plus the constraint number 2. This whole thing now is in canonical form. So we find a linear programming problem in canonical form. It's a problem that we just decide to minimize that guy. The meaning will come soon. So if it's in canonical form, that's good news. That means I can give this as the starting point for the associated simplex algorithm. I can try to solve it. Is that right? The algorithm will kick in. Okay? So this could be it's the starting point. It's the initial point for the associated simplex algorithm. Okay? Algorithm for this problem. Okay, and then you can go to LP Assistant, or you set up the Tableau, you solve it by hand, you keep pivoting until you find the minimum for this W. And you can solve this problem. Is that right? In favorable cases. Presume that no trouble occurs. All right. Okay, let's say we solved it. Okay, we will solve it. And then we probably should think a little bit about, make some observation, do some discussion to see what are we actually doing? What do we expect? If we solve this and we get certain answers, what does that mean? All right? So let's do a little bit discussion to see. Okay, so what are we solving? We are minimizing W, which is the sum of all these artificial variables. So a few discussion here. So since I know now W is just summing up all of these with the positive coefficient in the front, and then I know in the problem all these variables cannot be negative. Is that right? So immediately I know this has to be bigger than equal to 0. Is that clear? So the minimum of W will not be negative. Is that right? For sure, because that's not possible, right? That's what we assumed it. Okay. So W min, we conclude, can't be negative. That is one observation. Okay, now second observation. Okay, we're trying to build some connection between our minimization problem to the constraint in set 1. Okay, now let's think, if I'm in the situation that the constraint in 1 is feasible, meaning there is a feasible solution to it, okay, what would that imply? So if now the constraint set 1 has a feasible solution, okay, what would that say to me? So let's say, what should I call it? Okay, let's just call it x1 and star, x2 star, all the way to xn star. Let's say that is a feasible solution, meaning if you plug that into the system 1, all equations holds, and these are non-negative, right? That's a feasible solution. Okay. Then what does it say to my LP problem? In particular, what does it say to system 2, and in particular to this W minimum? So if this is a feasible solution for 1, let's look at how 2 is different from 1. If I plug in that solution, x1 star, or in here, that means this will equal to B1. Is that right? And this will equal to B2, and then this part will equal to Bn. What will we conclude about these artificial variables? They have to all to be 0. Is that right? Okay. So this means I find a solution for 2 based on that will be x1 star, x2 star to xn star, and 0, 0. I find a solution by just that. And is this feasible? Is there any negative number here? No, because this is feasible, so this is non-negative, and I add a bunch of zeros, it's non-negative, right? So this is actually a feasible solution for system 2. Is that right? So what is the value W at that solution? What does W equal to at that solution? What is W? Is the sum of all these. Is that right? So W equals to 0 at that solution. Is that right? And now thinking the discussion at step 1, we say W min cannot be negative, and you find a point where W equals to 0, and that has to be the minimum. Is that clear? Okay, so we would conclude that now W min equals to 0. Is it clear? So if the initial system 1 is feasible, it will lead to minimum of W equal to 0. Okay? And so what I'm trying to build here is actually a equivalency between those two. Now I'm trying to go back. Now, okay, let's say I solved the linear programming problem trying to minimize W, and I carry through simplex and pivot, and in the end I found that W min equals to 0. What does it say to me? Okay, so let's say I have the opposite starting point. If now I found out W min equals to 0, what can I conclude? Okay, if W min equals to 0 at a basic solution somewhere, at a point, let's say a feasible solution, let's write it out, say, just give it some index. Let's say, can I use tilde, x1 tilde, x2 tilde to xn tilde, and then xn plus 1 tilde, all the way to xn plus m tilde. Let's say I find minimum of W is 0, and it's attained at that solution. Okay, what can I say? Then what must be true? So first let me ask you, what will these axes be? They have to be all 0, because W is the sum of them. Is that right? And now, at that point, W is 0, and they are non-negative. They have to be all 0. Is that clear? Okay, then we know xn plus 1 tilde equals to all of these. They must all equal to 0. Is that okay? And then what does it mean? Okay, so you see you have a solution where all of these are 0. And okay, the first n, I don't know what they are. They're probably not 0, which means if I plug in these in here, the first n, into the system number 2, I will have this plus that. This is 0 equal to b1, and then all the way through, that's 0 equal to bn, which means the 2 simply reduces to 1. Is that right? Which means if I only take the first n of this, x1 tilde, all the way to xn tilde, that must solve system 1. Are you with me? Is a solution for 1. Is that right? And then is this solution feasible? Okay, this, you take that from a feasible solution. These are non-negative, right? And then 1 has a feasible solution. Yeah. Is that okay, this argument? So what have we shown now? We have shown that if 1 has a feasible solution, then W min must be 0. And also, if W min equals to 0, then 1 has a feasible solution. So what does it mean? These two statements are equivalent, right? One implies the other, and also the other way around. Is that clear? Okay, so let's write this down. We have this conclusion. Okay, so these two statements, so I has a feasible solution is equivalent to W min equals to 0 for this for the LP that we set up, star plus 2. So that's equivalent. So this gives us like a kind of a flag, some kind of a double check. Is that right? If I manage to drive W min to 0 as the solution for that problem, then I know the original problem is feasible. There is a solution there. Is that clear? And then the opposite also holds, right? So furthermore, now, if somehow I solved the problem for the minimization and I find out that the W min is strictly bigger than 0, what can I conclude? So this is 1, 2. So by logic, if A and B are equivalent, then not A means not B. Is that right? So this would imply the original constraint is not feasible. So there will be no feasible solution at all. Okay? So this process gives you additional information. You can even use it to check if the original one is feasible or not. Okay? Okay, so all that discussion now gives us a suggestion for an algorithm, also at least the first stage of the algorithm. So this is called stage 1 because we're dealing only with the constraints now. We have not put in the original LP, only the constraints, and we want to rewrite the constraint in canonical form. Okay, so now instead of solving 1, I could solve this linear programming problem by simplex method. So, and if I solve this, solving star plus I, plus 2, will give me a feasible solution for the first problem. Is that right? So solving that gives a good solution, so feasible solution to the problem 1. And if you solve it by the simplex method, by doing pivoting, either by hand or using the LP assistance, and you will be solving it. So here's the next argument. When you find the solution by our argument here, the artificial variables will all have to take value 0, right? That will be if W reached the minimum 0. These will all have to be 0. So when a variable is 0 in a basic solution, that means this variable could be taken as a non-basic variable. They take value 0. Is that right? So which means in the simplex algorithm, by pivoting, you would have replaced all of these by something here. They will be getting out of the set of basic variables, and you will have a set of basic variables using the original variables. Does that make sense? Mm-hmm. And then the pivoting process will put it in canonical form. Is that right? All right, so that's the second observation. This pivot process will put 1 in canonical form. Okay, so that is what we wanted to do, right? We want to do the constraint into canonical form. Okay, this process can be done by hand or by LP assistant, and then you will have your constraint in canonical form, and you can just manipulate your original objective function and put the original LP in canonical form, and this could be the starting point for the second stage, stage 2, which we will specify. For stage 2, meaning you can start to solve the original linear programming problem. Okay, so that's the big idea, but let's take some examples to see what I mean. Is that okay? Let's do that. Okay, I will take an example where we only deal with the constraint, okay, just to get us familiar with this process that we just introduced. And then we'll connect it with linear programming. Okay, so here's an example. Okay, so it's understood. I want you to use this technique, all right? Put the following in canonical form and find find some non-negative solution. Okay, so we need feasible solution. We want it to be non-negative. Okay, so let me put up the system. It's 2 equations to be simple. Okay, we have these 2 constraints, 3 variables. We want to put it in canonical form and find a non-negative solution. Okay, is that all right, what we're trying to do? All right, so using the technique we have here. So we have to add artificial variables, 1 for each equation. So x4 x5, and they are both bigger than 0, right? And we would let W to be the sum of them. Is that right? That's the one we want to minimize, right? So then we have the following problem. Minimize W, where I'll have the following. So I will add x4 on equation 1 and x5 on equation 2. Okay, so I have the following. x1 minus x2 plus x4 is 1. 2x1 plus x2, x3, x5 equals to 3. Okay, those are the constraints. And I would like to write out the equation for the W, the one I'm trying to minimize. And I will use this form here, that I'll just add the coefficients in each column here and take the negative value of the sum. Is it okay? So here I have 1 plus 2 is 3. I need to put negative 3 x1 for the W, okay? And negative 1, that's 0. So 0 x2. This is negative 1, which I change sign into x3. So okay, I can probably do that. After this is these are the artificial variables, and I should not put anything here, right? And that will equal to 1 plus 3 will be 4. I'll put it into negative 4 plus W. Is it clear how I get this equation? Everybody, any questions about where I get that equation from? Is clear? We're good? All right. Okay, now this is in the form that I can put in a tabular form or in LP Assistance and carry out. So let's practice on that and make some observation, of course. Okay, so let's put it in tabular form, which I did, and I copy it. x1, x2, x3, x4, x5. Okay, and I know the basic variable right now is x4 and x5, right? That's the way we set it up. Okay, so let's put in the numbers. 1, negative 1, 0, 1, 0, 1. 2, 1, negative 1, 0, 1, 3. And then for W, I'll have negative 3, 0, 1, 0, 0, negative 4. This is just linear programming, right? I'm minimizing W right now. Okay. So anyone wants to guide me? Where should I pivot? If you're in LP Assistant, where would you click? Which column? X1. Which position? For X4 or X5? X4. Because the ratio is smaller. Is that right? So what does it mean? I will replace X4 by X1 in the basic variable, right? So now I will have X1 and X5 here. Okay, and you carry out that pivot process. Okay, so 1, negative 1, the first one is unchanged, and the second one changes into 0, 3, negative 1, negative 2, 1, 1, and 0, negative 3, 1, 3, 1, negative 1. Okay, let me draw a dotted line to separate the artificial variables from the rest. So you know, those are artificially added. I'm trying to get rid of them, all right? I just use them to help me getting into a canonical form. Okay, now, are we done? Should I pivot further? Which column? This is negative, is that right? Okay, so which one of them I would choose? There's only one positive one. Is that right? So which means x5 will be replaced by x2. So I got rid of the second artificial variable in the set of basic variables, which is good because that's what I want to. I want to get rid of them. Okay, so you pivot right there, and we'll get the following. So I have 1, 0. Now I get some fractions. 4/3, 0, 1, negative 1/3, negative 2/3, 1/3, 1/3, and then I get 0, 0, 0, 1, 0. Okay. So am I done? Do I have any negative numbers here? No, which means W has reached its minimum at this basic solution. Is that right? What's the minimum of W? Did we drive it to 0? Yes. So we see that W min is 0. That means the original problem has feasible solutions. Is that right? And then the problem is asking you to, let's put that statement. So let's call that star. Oh no, we're using stars. What should I call? Okay, 1. So which means 1 is feasible. If it's feasible, there shall be a solution, right? How can we rewrite this 1 into canonical form? So at the basic solution where W equals to 0, we know that x5, x6 will all have to take value 0 because they are non-basic. Is that right? And when you rewrite out the equation for x1, x2, and x3, what is relevant in that table, let me use a color chalk to, I did bring color chalk. Okay, use pink. So how would I extract out the canonical form for x1, x2, x3? Well, it's here, isn't it? Because x4, x5, they'll all be 0. So I will have equation for x1, x2, x3 with these coefficients and with this part on the right-hand side. Is that right? Is that step clear? So let's write out. Now, canonical form will be the following. Okay, let me go up there. You can't see if I write so low. Okay, so only the red box area is needed, okay? So I have x1 minus 1/3 x3 equals to 4/3, and x2 minus 1/3 x3 equals to 1/3. Now that is the canonical form. Is it clear where I get these information from? Okay. So what is the associated basic solution? So the basic solution. You know it has to be feasible because the right-hand side is all positive, right? What's the basic solution? Can you tell me what will be for x1? Isn't that the right-hand side? Is that right? x2 and x3, 0. Okay. And that is feasible. It's non-negative, right? Is that okay? That's an example on how this technique works, and by solving this minimization problem, you manage to drive the original problem into the canonical form, which you can use now to solve the original minimization problem for Z. All right? And then you can initiate the simplex method. Is that clear? So that's a step. Okay, so Okay, so you can use software or you can use by hand, and let's make an observation. If I manage to drive W down to 0, in the end, the information that's needed for me are in these red boxes, okay? Which means the information outside, they are irrelevant. I don't need it at all. In particular, after here, this part, this pivoting part on x4, x5, on the artificial variable, has no saying in the end, or these, right? So if you're doing it by hand, you could set up like this. You don't have to compute these values. All you need to do is compute these values and see that you drive it down to 0. Is that clear? Save some work. But if you use the software, it wouldn't mind to compute the whole thing. Then you just click at the correct spot to pivot. Is it okay? All right. So that's that example. And now I want to show another example. Now we will connect this to a minimization problem. Okay? So, okay, I think this is actually taken from the textbook. There are lots of words in the textbook you can read. If I didn't say enough. Did I talk enough? No. Okay, so I want to minimize that. Subject to the following. Okay, this takes a long time to write down, but okay. Three. Okay. I think it's from the textbook. Now we want to solve the whole problem. We'll go through 2 stages. Stage 1, we will drive this into canonical form. And then stage 2, and we solve the minimization problem. Is that clear? Okay, so stage 1, we'll actually do stage 1 by hand, and stage 2 will go to the software. So stage 1, I need to introduce artificial variables. So artificial variables, I will introduce 2 of them, x5, x6, because I need 1 for each equation, so it can be canonical, and then W will be the sum of them. Okay, that's what we always do. So I can rewrite this into the following form. So x1, okay, this is copying. So I add an x5 to the first equation, and it equals to 3 on the right-hand side. And the second equation, And then in principle, I could put the equation for z here also. If I do that, let me just write it here, but okay, I might not take it with me in the table, but I want to make a point. That should be 0 plus z, is that right? And then I will write out the one for w. W is x5 plus x6, so I know I need to add up these coefficients and make them negative. Is that clear? I add this up, 2. I get negative 2, x1. Add this up, negative 3, so 3, x2. Add this up is negative 1, so it's 1. And then add this up is negative 1, so it's 1. Okay, and this should be nothing here. And then the right-hand side added this up is 14. Right? So I have all the information there. So stage 1, I will minimize w, use this as objective function, and use these first 2 as my constraint. Is that right? Okay, so let's see if I can carry this out. Okay, so don't take the z term with me. So the first step is to minimize w. Okay, so it will drive the original equation system into canonical form. All right, so let's put it in the tableau. x1, x2, x3, x4, x5, x6. Okay. Okay, so right now I have x5, x6 as my artificial variable, basic variable is artificial. Let me put in the numbers. 3. $11. Okay. Yeah, well, I could have, okay, let me kind of intentionally leave some space, but I'm not going to mess it up actually. Okay. I want to drive this guy to 0, right? That's my goal. And I check these coefficients, and I found a -1, and I will find a spot to pivot. Is that right? So I will take this one to pivot because 3 is smaller than 11. Okay? And if you perform that, so I will have x1 and x6 as my new variable. So I will have 1, -2, -3, -2. I'm not going to copy down here because they're irrelevant. 3. And then for x6, I make that 0, 1, 5, 3. And I have 8. And the w term becomes 0, -1, -5, -3, and -8. Okay, that's after one step. And now I see I have 3 negative numbers, and this is more negative than the other. It's a bigger negative number. I'll choose this column, and I found a positive coefficient to pivot. Is that clear, my choice? That's where you would click in the LP assistant. Okay. And then you see if I add this on top of that, it gets all of these 0 and get that guy 0. Okay, so let me write this down. So now I have x1, and then x3 will replace x6. Okay, so I have 1, -2, -3, -2. Oh, no, that's wrong. I have to pivot. Sorry. I will have to pivot. I will add this on top in a correct number. So 1, 0, 7, 4, 19, and 1, 0, 5, 3, 8. And then if I add everything down here, you see I get 0, 0, 0, 0, and 0. Okay? These numbers don't matter. Okay, so what does it mean? This means now I rewrote the constraint in canonical form using x1 and x3 as basic variable, and I have a feasible basic solution. Question?
Did you pivot x2 or x3?
x3 to replace x6 because the -5 is bigger in absolute value. It's more negative. That's the algorithm. You could pivot anywhere. It will lead you to the same thing eventually. It should. If the original problem is feasible, this process will lead to a canonical form. Question?
I think she means that when you added, you treated x2 as the variable you pivoted. So like
Where?
From x6 to x3, that row you're using,
Uh-huh.
multiply x6 by 2, and then add it to the first one, you'll get 7 and 4.
Oh, you're right. Yeah, sorry, that's my boo-boo. Okay, okay, so I did there. It doesn't matter. It will lead you to the now I have x2 here. It will drive this in canonical form. You can pick any of these in principle. The goal is to get rid of x6, right? Thank you. That was, yeah, I put my circle too fast. Yes, on my note, I am circling there. Well, okay. All right. Okay, now I am in canonical form, and you can initiate stage 2 now. Is that right? I can go to stage 2. My constraints are already in canonical form. The only thing that I need to manipulate a little bit is the objective function, z. Is that right? But then, you see, if I carried that row for z with me here, and I did the pivoting together with the z, then the z will have all 0 in front of coefficients. That's basic variable because it will be pivoted. So what I want to say is that the whole process actually could be very much streamlined, and I could put the whole thing in one tablet, right? So I'm going to show you how to do this using the LP assistant. This process of adding artificial variable is built in there. So, okay. Okay, it's warming up, and let me put the problem in as we're waiting for the projector. So, 1, -2, -3, -2, and 3. Can we see? Can you see what I'm doing? May I turn off the front? Will that be okay? You have lights, right? Okay. So I am putting in the initial problem that is not in canonical form. Okay. So the first equation I put in. So the second one I put in 1, -1, 2, 1, 11. Is that right? And then what I put in will be for the z coefficients 2, -3, 1, 1, and the last one is 0. So this is the original constraint, and where none of them from x1 to x4 can be used as a basic variable. It's not in any canonical form, right? So now we introduce the artificial variables. So how do you do this in the LP assistant? So you notice that I have not specified the basic variables. They will be taken by the artificial variables we're going to introduce. So you're going to click on that X, and it will pop up this window. And then you say, I need to add an artificial variable right there. And you click on that, and then it gives you an X5, which will be the basic variable here, and it's an artificial one. Is that clear? And then for this one, I need to add one also, because I don't have any ready for me. So I add another one. So it chooses x5, x6 as the basic variable. And it prepares this table for you like this. And the area that's shaded, that's kind of a yellow-orangish, that's the part all dealing with these artificial variables that you just add on. All right? So you see this is 1, 0. And this line here, the row below the z, that is the row to solve the equation for w. Okay? The w now takes the value 14 at this, when x5, x6 equals to that, and where all these x1, x2, x3, x4 are 0. Okay? So now we are ready. So we can initiate the pivoting process. Now what you need to do, well, I need to drive this guy to 0. Is that right? I want to minimize my w. I want to make sure all of these are non-negative. Is that right? So I'm in stage 1. So I find a negative one. I chose which one is smaller, this smaller, so I pivot right there. I give a click. Let me open the windows a bit bigger. Okay? And then it did the pivot process for me. So I have this table. So this will be the same as the one I had on the blackboard, except it added this row for the z. On the blackboard, I didn't include the z. Now these together being pivoted. It's all streamlined. Okay? Two stages, but in the same tableau. All right? Okay, now I see I have -1, -5, -3. You can pivot on any of these. Shall we try to pivot on -5 and see what it actually comes out? All you need to do is choose to click here or to click here. It will do it for you. All right? Let's click right here. Click. Tuck. Now, let's see. Is the W now down to 0? Yes. Do I have any artificial variable in the basic variables? No. So I'm done with stage 1. Is it clear? Stage 1 is done, and the original constraint now is in canonical form with x1 and x3 as the basic variable. Is that clear? And then conveniently, the z is also prepared so that it's written in terms of the non-basic variables. Is that clear? This is the end of stage 1. Okay, and then we need to check which one of these is negative. If it's all non-negative, I'm done. If not, I need to pivot. So I find a non-negative guy here. And then in this column, there's only one that's positive, right? Do we agree we need to click on that one? Let's click. Okay, and then it gives me this table. And then I see I have 0, 0, 2, 2. I don't have anything negative, which means I have found the z min. Is that clear? And that's how it is done in the LP Assistant. So what the LP Assistant does for you is nothing but carrying out the pivoting process. You are the brain behind where to click. If you click at a different spot, it will go to different answers. Okay, so it's just some assistant. It's not a complete automatic program that will minimize things for you. Is that okay? So is it clear? So in the end, and at the end of stage 1, if you're doing it by hand, then you don't have to carry these yellow shaded part with you because they don't have any meaning anymore, right? But okay, in the program, it doesn't take any time to compute one extra column or row. So it's there. So you have to be able to see in this table where are the relevant informations to subtract. Okay, so let's write out from this table what do we have. Okay, so I'll just turn on the light and let's write out the solutions. Will it be better I do it here? Can we all see? I will just use a very narrow strip too. All right, so we see that stage 1, you shall be able to read this chart and tell me what's happening in this chart, okay? Stage 1, we see that we have driven W down to 0. That's the minimum, and then everything is non-negative here, right? So stage 1, we found out W min equals to 0, which means the problem, and the original problem, did I call it 1 or did I call it star? Okay, let's just say LP is feasible. The constraints are feasible. That is solution. That is stage 1. Okay, you know where to look for the information and all that. Okay, and then stage 2, where do you find the information? So after here, then I will be looking for these coefficients and find the negative ones and figure out where to pivot, right? And then I did one pivot, and I found that these are all positive. So this will give me the answer for my original minimization problem. Is that right? So from stage 2, I realize now the minimum for z, what would that be? What's the minimum for z from this chart? How can I read that information from? You know it's coming from this position, but what is it? Min, z min is? What do I have to do with that number? Negative sign, right? I have to change the sign. Okay, and attained where? So give me an answer without the artificial variables. I only care about x1, x2, x3, x4. What will those values be to attain z, that 14? So tell me, what will be x1? How do you read it? x1 is 19. Is that right? And x2 is 8. And what's x3 and 4? Because they are non-basic. And then you complete. Is it clear, the 2 stages? Now, I am just curious. If I did not click on the 5 and I did as I did on the board, what would that be? Can we play a little bit with it? Let's remove. Okay, so on the board, I actually clicked here. Is that right? Will that lead me to the same answer? Are you curious? Let's see. Yeah. So it now puts put my W all into 0, and then the minimum is 0 here. So I completed stage 1, right? And I rewrote the problem in terms of the basic variables, x1 and x2. And then I will go to minimize the z, and then I see that these are all positive, then I'm done. Actually, 1 click. So maybe subconsciously I knew that would be a better choice. No, I wouldn't claim that. Okay, it's a mistake, but okay. So mistake on top of mistake, maybe it's correct. All right, any questions? Will we be able to use LP Assistant to add artificial variables? So this example is an example, and also all the example we saw today in class they are the examples such that in the original system you don't have any good candidate for basic variables. So we introduce one artificial variable for each constraint, right? But sometimes you might have some variables already pivoted that can be good for a basic variable, and then you do not want to add another one. Say you have 3 constraints, maybe you just need to add 2 more artificial variables. Okay, so next time we'll have an example like that. So you see partially artificial, right? Okay. Right, don't forget to turn in your homework.